have studied different base units, SI units of derived quantities, right? And how do we convert these SI units of derived quantities into base units? What are base units? Base units like mass, which is in kg, then time, which is in second, right? Then temperature, which is in Kelvin, luminous intensity in terms of candela, then what? Time in second, correct? Length in terms of meter. So we are deriving all the SI units of derived quantities in terms of our base unit. Okay, so let's start. Let's continue from where we stopped. So yesterday we studied so many concepts, right? Which were they? Can somebody brief? What all did we study in the previous class? What all have we derived base units for? Yes, children?
Illuminance,
Illuminance, correct. Then
activity,
activity,
absorbed dose,
very good. Then
and entropy, heat capacity, all that.
entropy, yes. Entropy, yeah. Joule, pressure gradient. Then what else? Luminous intensity, right? Then we have studied about
Magnetic
electricity,
flux.
magnetic flux, conductance, capacitance, electrical resistance, then force, right? Pressure, stress, all that we have studied in the previous class. Now, can somebody tell me what is Joule? What is Joule? We use Joule everywhere. No, what is this Joule? What is Joule, children?
Unit for work done.
Work done, right? Or energy stored, we can say. Energy. Now, some work is done, okay, when an object moves at a distance of 1 meter. Some force is applied. By applying the force, you are doing the work. Then only you say the work is done. So that work done symbolizes Joule. So work done may just not be to move any object. It may be in terms of charge as well. Work done to move a unit charge by, a potential difference of 1 volt. We call it as joule. Or work done to raise the heat, okay, to raise the temperature by 1 degree Celsius. That is also joule, right? So anything where the work is done, you call it as joule, right? So therefore, keeping this in mind, we have the next concept to derive, that is specific heat capacity. Okay, specific heat capacity. One important thing is, children, yesterday whatever we have studied, no, that is joule, watt, volt, coulomb, farad. Okay, whenever you are deriving any quantity, see that you have written down somewhere and it is in your mind. Okay, so these all quantities should be on the tip of your tongue. Coulomb, resistance, joule, Newton, okay, all the base units of these quantities. So that it's very easier for us to derive the rest. So that's why I also write here and keep off so that I may not miss out anything. Okay, so whenever you are studying also, see that you are not missing out on anything. All right, see that you have already prepared a chart. So prepare a chart. Yesterday in the group I have shared a chart, right? A chart on all these quantities. So these, see that you are, keeping it in mind, or make it as a big chart and stick it on your, cover or something. Every day you should have a look at it. So it should be on the tip of your tongue. All right. Okay, so let's start. The next quantity that we are going to derive is specific heat capacity. Now, what is this specific heat capacity? Now, when I'm talking about specific heat capacity, some energy is required to raise the temperature of 1 kg of substance to 1 degree Celsius, right? Now, specific heat capacity of that heat to raise the temperature by 1 degree Celsius is called as specific heat capacity. And it is measured, the SI unit for specific heat capacity is given by joule per kilogram. Okay, joule per. Okay, Iman is still joining. All right. Joule per kilogram Kelvin. All right. Why joule? Because work is done to raise the temperature, right? Now, why kilogram? To raise the temperature of 1 kg. Why Kelvin? Because by 1 degree Celsius. So, there is energy that is involved here, right? There is work done, and there is mass that is involved here, and there is temperature that is involved here. So therefore, we write the SI unit is nothing but joule per kilogram Kelvin. All right. So joule is represented by J divided by kilogram, kg, Kelvin. All right. We already know that kg and Kelvin are already the base units. So therefore, what do? We write joule. We know what is joule, children. Joule is nothing but Newton meter, right? Joule is nothing but Newton meter, and we have derived already the units for joule. That is kg meter square per second square. So kg meter square per second square divided by kg Kelvin. So kg will get cancelled. Remaining will be meter square per second square per Kelvin. Easy? Got it? Got it?
Yes, ma'am.
Yes, ma'am.
Okay. So after knowing about specific heat capacity, next we will study about. See, I'm trying to get this thing. What is that? Pen board. Okay. So that I know that is the screen little blur or is it very clear?
Yes and no. It's blurry and clear at the same time. It's kind of okay.
Okay, yeah. So
Yeah.
I ordered pen board so that I can teach easily. So till then we just adjust children. Okay, try to understand something. Yeah. So
Ma'am.
I have also created videos. All right. So if ever you have any doubt in any concept, you can go back to that video and check out. All right. Yes. So let's go ahead then. We are going ahead with the next SI or the next quantity called as specific energy or latent heat. Specific energy or latent heat. Now, what do you mean by specific energy or latent heat? It is nothing but energy per unit mass. How much energy is there in that per unit mass? So 1 unit of mass, how much energy is stored? That is nothing but specific energy or latent heat. Okay, so how much energy is there per unit mass? Energy per unit mass. Energy per unit mass is called as latent heat or specific energy. See, energy can be anything. It might be kinetic energy or potential energy. Potential energy per unit mass or kinetic energy per unit mass in terms like, or you can write both potential and kinetic energy together. So therefore, specific energy is nothing but how much energy is stored in that per unit mass. All right. So we give it as joule per kilogram. The SI unit given to us is joule per kilogram. Okay. So why joule? Because there is energy involved. Why kilogram? Because mass is there. Right? Energy per unit mass is nothing but what? Energy per unit mass is nothing but joule per kg. Right? Now what is joule? Joule is nothing but we know Newton meter, that is kg meter square per second square divided by kg. Right? So therefore kg gets cancelled, remaining meter square per second square. Clear? Clear? Easy? Easy? Or no?
Yes, ma'am.
Okay. See, only with you this answering children, I want everybody to answer as well. Okay? Or else I won't know. Or maybe I'll just remove you from the meeting. Yeah? Next. Radiant intensity. Radiant intensity. Yeah. Before I go ahead with radiant intensity, now what is solid angle? Suppose, see, this is a circle, no? This is a circle, right? Circle is a 3D figure. Now, this circle, I will do a cone on this circle. All right? I have prepared a cone on this circle, right? Now, if I open this is nothing but the angle formed by this, right? This is how the solid angle looks like. If I do angle here, all right? So, if I just do this angle here, if I just write this as d theta, or what is that solid angle? D omega, d omega, all right? So this is nothing but one of the angle formed by this solid angle, right? Solid angle is always a 3D figure, okay, three-dimensional figure. So the angle formed by a three-dimensional figure is nothing but what? The solid angle. The area, this part is called as its area. This is the angle formed, this is its radius, and this entire thing is its area, that is dA. Okay? This entire thing is called as its area or dA. Alright, children? Or we also call it as they call it as d phi also. dA or d phi. So that is called as a solid angle. So radiant intensity is nothing but the radiant energy radiated from a point source per solid angle in the radial direction per unit time. That means how much radiant energy is emitted. Now, suppose this is the solid angle here. All right, there is certain radiant energy that is radiated from a point source. Okay, from a point source, there is some radiant energy that is coming per solid angle, per unit solid angle. All right, in a radiated direction per unit time. All right, so the direction is this way. So this way, when there's a radiated intensity coming into picture per this solid angle, what is the energy or the intensity, how how bright it is, that is nothing but the radiant intensity. Okay, so radiant intensity is nothing but radiant energy radiated from a radiated from radiant energy radiated from a point source. It may be anything. Okay, any point source, maybe sun, whatever. Okay, any point source, any source of light. All right, per unit solid angle, per solid angle, per solid angle in a radial direction per unit time. In a radial direction. In that direction at per unit time, that means per second, right? Radial direction per unit time. Per unit time. It's called as radiant intensity. All right. Now, radiant intensity is given by watt per steradian. Watt per steradian. Why watt? Because power, right? The power, radiant intensity, how powerful it is, how bright it is, the power. That is nothing but it is expressed in terms of watt. So watt divided by steradian. Why steradian? Because it is a solid angle, right? How much energy is radiated from a point source in that per solid angle? That is nothing but radiant intensity. Yeah. So therefore, watt is given by what? Watt we know that we have derived yesterday. It is kg meter square second cube per second cube, right? Kg meter square per second cube divided by steradian SR. Steradian is a supplementary fundamental quantity, right? So it does not have a derivative. Steradian is SR only. All right. So it is already a fundamental supplementary what is that quantity? All right. So therefore, we write the final base unit as kg meter square per second cube per steradian. Clear, children? Clear? Yes?
Yes, ma'am.
Yes.
Okay, good. Now, after knowing about radiant intensity, let us go ahead with the next quantity. That is thermal conductivity. Thermal conductivity. What do you mean by conductivity? Anyone? What is conductivity? Yes? Can somebody tell me what is conductivity, children? Conductivity. Normally, what is conductivity? What comes to your mind when I say conduction or conductivity? Yeah?
Ma'am, heat passing through a material or something like that.
Yeah, something is conducting there, right? Very good, Piyusha.
And the ability to allow something to flow through.
Yeah. So whenever we
Pass.
are talking about thermal symbolizes heat, right? How much heat is passed, how much heat is conducted in that material is nothing but thermal conductivity, right? Thermal conductivity is nothing but you can write the rate at which, the rate at which passes through, heat passes through, heat passes through a specified material. A specified material is called as thermal conductivity. All right. It is expressed as what? Watt per meter Kelvin. Watt per meter Kelvin. Okay, this is the SI unit. Watt per meter Kelvin. All right. So we know that watt is W divided by meter is M Kelvin. Okay. Watt is nothing but what, children? Kg meter square per second cube divided by meter Kelvin. Now there is meter square, there is meter, that is m raised to 1. So m raised to 2 divided by m raised to 1 is what? M raised to 2 minus 1 or m raised to 1. So therefore, I can write kg m raised to 1 per cubic second per Kelvin. Right? I will take it up. It will become per Kelvin. Easy? Got it, children? Yeah?
Yes, ma'am.
Oh, good. Good, Neha. Yes. Now let's go ahead with the next quantity, that is energy density. Energy density. Energy density. What is density? What is density?
Mass by volume.
Mass by volume. Very good. Can somebody give me an example for density? What is density? Why does a needle sink but a ship float? What is density?
Mass by volume.
Because
Yes? No, according to me, now ship's mass is big. So why does it have to float? Why doesn't it sink? Whereas the needle is a small thing, right? It has very small mass. But why does it sink? Why it sinks? What is this density?
Mom,
Yeah.
is it
because
because
the
like
density of needle
Yeah. Yeah, Piyusha, you talking? Density of
a needle is less than the density of water.
density of needle is less than density of water, then needle should float. But why does it sink? True?
um I'm not sure, Mom. Like
See, density is nothing but mass by volume. Yeah, we all know that density is nothing but mass by volume. What is this mass by volume? Mass by volume is, now suppose I have, less mass. Okay, suppose I have less mass and more volume. What do you mean by less mass and more volume? What is volume? What is volume?
Space occupied.
Correct. The space of. Now suppose there is a needle. Okay, suppose this is a needle here. Okay, it has certain mass. Okay, and needle also has certain volume. So whenever I take mass by volume ratio, mass by volume ratio is greater than 1. So whenever mass by volume ratio is greater than 1 for any kind of, an object, it always floats because water's density, that means density of water is less than 1. All right, or equal to 1. Whatever object's density is greater. So suppose it is heavier, its mass is also bigger and its volume is also more. So mass by volume becomes greater, right? That is why the needle sinks. Whereas ship, what happens? Mass by volume, the ratio, mass is more. Okay, volume is also much more. So therefore, mass by volume ratio is lesser than the density of water. Density of water is greater than the density of what that ship and that ship of mass of that ship and the volume is. So that is why it flows. Okay, if the density is lesser of any quantity, then only it flows. If the density is greater than the quantity, then it sinks. Okay, what is density? Mass by volume ratio. Okay, so how much mass is, if that much volume it has, then definitely it will sink, right? That is its density. It has that much density in it, right? Now, but what is the lesser density? Lesser density means it does not have much density. Either one quantity is less, either its mass is less or the volume of it is less. It's not greater. It's not equal. Okay, if there's so much of mass, there's not so much of volume. That is when I say that the density is less. Okay, either one quantity is less. That is why it begins to float. Whereas needle, mass by volume density is greater than mass by volume density of water. That is why the needle sinks. Clear, children? Yes?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now, when I'm talking about electric charge density, what do you mean by electric charge density? Electric charge density is something, sorry, I'm not going to get it. Energy density, sorry. Energy density. What is energy density, children? Energy density is nothing but amount of energy stored in a given system or region of space per unit volume. All right, amount, how much energy is stored in that volume, that is called as energy density. You can write amount of energy stored, amount of energy stored per unit volume, per unit volume is called as energy density. All right, and it is given by, energy density is given by joule per cubic meter. Why joule? Because energy is involved. Why cubic meter? Because volume is involved. All right, joule per cubic meter. And what are the base units for joule? We know that yesterday we have derived base units for joule are kg meter square per second square divided by meter cube. Right? So there is meter square, that is meter into meter, divided by meter cube, m into m into m. So 2m cancel, 2m cancel, so it will be 1 by m, which is nothing but m raised to minus 1. So instead of m raised to 2 divided by m raised to 3, can I write m raised to minus 1? Yes? Yes? Yes,
Yes,
or no?
ma'am.
Yeah. So therefore, kg per meter per second square is the base unit for kg per meter. Got it, children? Got it? So energy density is nothing but how much energy is stored per unit volume. Mass by volume is density. But what is energy density? How much energy is stored per unit volume. Clear? Easy? Yes or no? Understanding, children? Understanding the concepts?
Yes, ma'am.
Yes, ma'am.
Okay. All right. Now we'll go ahead with the next quantity, that is electric field strength. Electric field strength. Now, what is electric field? What is electric field? What is electric field? Yes. What is electric field? Are yes, Arshit. What is electric field, Baba? Someone. What is electric field, children? Ethan, Piyusha, Harshit. What do you mean by electric field? Someone.
Um, I guess maybe like a field which
That surrounds
electrons
electrical
maybe.
ma'am.
Yes. So, see, yeah, the field where any magnetic, if suppose there's magnetic effect, then the electric field is experienced around the conductor, right? So electric field strength, the strength of the electric field, how strong it is. That is nothing but the intense of electric field in a particular location is nothing but electric field strength. The number of charges that are passing through a conductor, right? So how much electric field do they produce, right? So therefore, this electric strength is nothing but how intense the electric field is at a particular location. That is nothing but electric field strength. All right, and electric field strength is expressed in terms of volt per meter. Volt per meter. All right. So volt is nothing but what, children? What is volt? Kg meter square per second cube per ampere divided by meter. So meter square and meter is here. So meter square means meter into meter divided by meter. Meter gets cancelled, so 1 meter remains here. So it becomes kg meter per second cube per ampere. Yes? So that is called as electric field strength. Electric field strength is nothing but how intense the electric field is at that particular point. Clear? Yes?
Yes, ma'am.
Alright, cool. Moving ahead, the next concept that we are going to study is electric charge density. Electric charge density. What is an electric charge? What is electric charge?
Ma'am, if not, could you repeat again? Your voice was breaking.
Yeah. So we are starting with electric charge density. What do you mean by electric charge? Electric charge. What is an electric charge? Yes? What is electric charge? Someone?
It experiences of force like when it is in an electromagnetic field, I think.
Yes, that's right. That's right.
Guess, ma'am, I guess a physical.
Yeah. Correct, Neha. You're telling something? A physical? A physical?
No, it was just the same. No. I thought maybe it was a physical matter of force.
Yes. So basically, a charge is nothing but one force is experienced by it when it is kept in a electromagnetic field. So that is called as charge. The substance which experiences the force of electromagnetic field is nothing but charge, right? So therefore, charge, electric charge density. Electric charge density is nothing but amount of electric charge per unit length. Okay? Amount of electric charge per unit length. Per unit length is called as electric charge density. Okay, children? So therefore, I can write amount of electric charge per unit length can be expressed in terms of what? The SI unit given to it is coulomb. Coulomb per meter cube. Alright? Coulomb per meter cube. We know that coulomb is what? Ampere second divided by meter cube. So this is nothing but ampere second per meter cube. Easy? Got it? Yes, children? Yes?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Please respond to me, children, or else how I'll know that you understood. Yeah? Okay. Now, electric flux density. What is electric flux density? The next concept is electric flux density. What is electric flux density? Electric flux density is nothing but electric charge generates the electric field, right? Or the strength of electric field is nothing but the electric flux density. How strong is the electric field? Okay, the strength of the electric field is nothing but electric flux density. So you can write electric flux density is nothing but the strength of the electric field. The strength of the electric field. The strength of the electric field is electric flux density. Is electric flux density.
Ma'am,
The
I have a
strength.
question, ma'am.
Yeah, Baba, tell me.
Ma'am, if like the definition of this is strength of electric field, then what is the difference between electric field strength and electric flux density? Because like,
Electric
aren't
field strength. Yeah. So electric field strength that we have studied is the intense of electric field at that particular location, right? How strong
okay,
it is at that particular. But electric flux density is all the electric lines of force. Flux. Suppose this is an area. At one point is nothing but how much this location experiences. That is electric field density. But flux density is total lines of force. Okay, total electric lines of force. The total that they experience. That is flux density. If only at a particular location, that is electric field. How much it experiences a particular charge. But flux is nothing but total electric field experience. Clear?
okay. Yeah, thank you, ma'am.
Okay. Okay, so electric flux density is nothing but what, children? The strength of electric field. The total strength of the electric field is nothing but electric flux density, and it is given by coulomb per square meter. Coulomb per meter square. Okay, so this is nothing but, again, coulomb is nothing but what? We know coulomb is ampere second divided by meter square. This is nothing but ampere second per meter square. Clear? Clear? So the difference between electric field strength and electric flux density is, here it is volt per meter, how much potential difference it carries, right, in electric field. That is when we say that it is, yeah, it is an electric field. Once we know that there is potential difference between that. But flux density is nothing but just it depends on charges. Okay, completely charges. That is why we write coulomb per meter square. Clear? Clear, children? Yes?
Yes, ma'am.
Yes, ma'am.
Yes,
Okay.
ma'am.
Now we'll go ahead with permittivity. Permittivity. The word itself is what? Permission. Give me some permission, madam. Or give me some permission, sir. Right? So permittivity. The next concept in physics is permittivity. What is permittivity? Permittivity is nothing but the ability of a substance to store the electric charge in the electric field. How able it is, how much it is permitting, right? So how much it is permitting a substance to store the energy, the electrical energy in an electric field. That is called as permittivity, right? So again, I repeat, the ability of a substance, how able the substance is to store all the electric charges in that electric field. It stores all the electric charges in that electric field. What is its ability? Is that is nothing but permittivity. All right, and the name, the SI unit given to it is farad per meter. Okay, farad per meter. So what is farad, children? Yesterday we have studied what is farad. What is farad?
Ma'am?
Farad capacitance, right? Capacitance is measured in farad. So what is the capacity of a particular substance such that it stores that electric field, right? It stores all charges in that electric field. That is called as permittivity. So SI unit of permittivity is capacitance per meter, all right, or farad per meter. Farad is nothing but what we know it is ampere square second raised to 4 per kg per meter square divided by meter, right? Then, so yes, divided by meter, right? Am I clear? Is that the one that we studied for farad? No, not per meter. This is divided by m, yes, right? So farad is just ampere square second raised to 4 per kg per meter square, okay, divided by m. So this is nothing but ampere square second raised to 4 per kg, m raised to minus 2 divided by m raised to 1. So if m raised to 1 goes up, it will become m raised to minus 2 minus 1, m raised to minus 3. Clear? Clear? So this is called as permittivity. What is it? What is it called, children? It is called as permittivity. The ability of the substance to store all the electric energy in that electric field. How much capacity that substance has to store the electrical energy. Next concept that we will study is permeability. 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 Okay. What is permeability? Able to be penetrated. Okay, how able it is for some substance to be penetrated. That is called as permeability. Okay, so or pass through, especially a liquid or a gas. How able a substance is such that anything can get penetrated into. So that is given by Henry per meter. The SI unit of permeability is Henry per meter. Okay, what is Henry? Yesterday we have studied. What is Henry? Weber per ampere divided by meter. So it becomes Weber divided by ampere meter, correct? Weber divided by ampere meter. Now what is Weber, children? What is Weber? Weber is nothing but joule per ampere, joule per ampere divided by ampere meter. So it becomes joule. I just erase this part. So it becomes joule divided by ampere square meter, right? So, yeah. Therefore, what is joule? Joule is nothing but kg meter square per second square divided by ampere square meter. So, meter square meter will get cancelled. It is kg meter per second square per ampere square. Clear? That's it. So, later we have only molar energy, still 4 more quantities, and then we are done with this part. Okay.